welcome back to this course on analog electronic circuits. Myself Pradeep Mandal, associated with Electronics and Electrical Communication Engineering Department of IIT Kharagpur. So, we are still revisiting some of the prerequisites, and today we are going to talk about MOSFET device, which is essential part of the analog electronics. And so, we will start with some basic concepts. So, let us see what are the overall plan we do have. So, we are going to start with basic structure of the MOSFET, particularly in MOSFET, and then we will be moving to the operating principle along with the biasing arrangement of the device, and then we will be going little detail of the IV characteristic of NMOS transistor MOSFET, and then we will be going to graphical representation of the IV characteristic of the MOSFET. And this module, it is having essentially two parts. One is related to N MOSFET, or rather N channel MOSFET in the first part, and then in the second part we will be having P MOSFET. So, we will be subsequently we will be covering P MOSFET. Many of the concepts here for N MOSFET, it will be applicable for P MOSFET as well, but there will be definitely certain differences. And after that we will be addressing some of the numerical problems to give you an idea that how the IV characteristic equation can be deployed to solve analog electronics containing MOSFET. So, the overall plan, again we will be seeing that with respect to our overall plan, where do we stand. So, as you said that we are in the components or device level, and we are still covering this week 1. We already have covered BJT, bipolar transistor, and today we are going to start MOSFET. And the plan is, as I said, that we will be going into the basic structure and then operating principle, characteristic equation, equivalent circuit later on we will be seeing, but at least we will be going up to the characteristic equation. And then as I said that today we will be covering N channel MOSFET, or it is called N type MOSFET, and in the next part we will be covering P MOSFET. So, let us see the basic structure of say MOSFET. So, as we said that we are going to start with the basic structure of the MOSFET, and here we do have the basic MOSFET structure. MOS stands for the metal oxide semiconductor and field effect transistor. So, of course, we do have the structurally we do have metal, then silicon dioxide, this insulator, and then we do have the semiconductor. And in addition to that, the field effect transistor, where from the control input we apply voltage to create field on the channel, which is supposed to modulate the characteristic of the channel. So, here the controlling element is basically electric field. So, that is why it is referred as field effect transistor. Whereas, for BJT, instead of applying directly voltage, we may say it is a combination of voltage and current, and in fact, it controls the current in the output port by applying current to the controlling port. So, that is a basic difference of MOSFET with respect to bipolar junction transistor. Anyway, so the MOSFET, before I go to the basic structure, the MOSFET, it is a very important element in today's context. In fact, for analog circuit, of course, BJT is a better option compared to MOSFET. However, in the recent scenario or in the present situation, what we have, it is whole system, it is getting integrated, and the system may be having analog and digital. So, you may say that in a system, if we are having say analog counterpart and then also the digital part, and earlier when analog and digital, they were implemented differently, maybe analog portion, it was sitting in one chip IC say 1, and the digital portion, it was in IC 2. So, based on the technologies, whichever it is suitable for digital, we were able to select that process to realize this IC 2. Likewise, whatever the process it is suitable for analog circuit, it was used to implement this analog IC. And invariably, as I said, that BJT is preferred one for analog implementation. And as long as these two ICs, analog and digital ICs, are independent, it was having fair good option to go for BJT. However, in last say 2 decades, in fact, it may be more than that, the analog and digital counterpart of a system, they are getting integrated together within single IC. And if we consider it is getting implemented within single IC, then we have to see which technology is better. Now, BJT, of course, BJT's technology, it is it may be good for analog, but definitely for digital, that may not be the good option. In fact, MOSFET, it offers many advantages for realizing the digital circuit. As a result, as the digital, with progress of time, as the digital portion of the whole system, it is dominating, naturally the priority is given more towards the digital circuit to decide the fabrication process. And this IC, the combined IC, of course, the MOS technology, where basic devices are MOSFET, is preferred one. Now, so the in this scenario, the analog circuit, which is of course, it is part of the same system, and if we want to make the system on single chip, then this analog circuit need to be implemented in the same technology, means the analog circuit need to be realized by using MOSFET transistor. So, whenever you are covering the MOSFET, is basically preparing ourselves for technology down the line, particularly mixed signal implementation of a system. However, as I said that BJT we prefer to keep because at the board level implementation, BJT implementation is better, where we can verify some of the basic concepts, whereas MOSFET normally it is not really frequently used for analog design on board. So, anyway, the now coming to the basic structure of the MOSFET, that as I said that it is having the metal oxide semiconductor. So, this portion, this is the cross section of the metal, and then the middle thin portion, it is the oxide, silicon dioxide. So, you can say this is oxide, and then this portion, it is semiconductor. So, that makes the MOS structure. Historically, this portion, it was metal, but later on it is observed that instead of metal, it is better to use polysilicon for tuning the threshold voltage of both NMOS as well as PMOS. Now, if you see here, we do have this is, as I said, that a metal, and this semiconductor portion, it is weakly doped p type semiconductor. And then we do have the two islands, two N plus islands, left side and the right side, and they are forming the I should say two terminal. And if you see here, this is N plus and then p weakly doped, though it is weakly doped, it is p type, and then we do have N type. So, you can say from this island to this island, it is complete isolation, and then by applying a voltage at the whatever this metal region, positive voltage with respect to the substrate, we can change the property of this portion, which is referred as the channel. And later on we will see that this provides very vital information that if we apply positive voltage, conductivity between these two islands can be modulated. So, as a result, you may say that this is the controlling terminal. By applying a voltage here with respect to the substrate p minus substrate, by applying a voltage here. So, in fact, electrically this p plus island is working as port for the substrate. So, if you apply voltage here which is positive, then you can change the characteristic of this region, ensuring that these two islands are getting connected. So, now if I see the conductivity between these two external terminal, that can be modulated by this voltage. So, that is the basic working principle. We will be going little detail, but structurally, as I said that this is having metal, oxide and semiconductor, and this is, I should say, it is though frequently in textbook it is referred as the MOS structure, but the actual view, if you see oblique view, it is shown here. So, I should say this is a front view or cross sectional view, whatever you say. You may say that this is front view, and this is oblique view. So, in this oblique view, what you can see here, so this is of course the metal portion, and then we do have the thin oxide. So, we do have the thin oxide here, okay, and then we do have two islands. So, we do have this island. So, this island, in fact, it is getting extended like this. This is also getting extended, and then we do have the electrically two terminals are there. And note that this substrate is weakly doped. So, if you directly try to access this substrate from top through metal line, that may create Schottky diode. To avoid the Schottky diode, what we can do, we can put p plus region, and then you will be getting ohmic contact. So, this p plus island is basically working as terminal for the substrate. It is referred as body. So, that is why we do have, we call this is body, we call this is gate, and these two terminal essentially they are interchangeable. They are in fact similar in nature, though this source is in this diagram it is shown close to this p plus region, but actually these two terminals can be interchanged, and depending on their voltage relative voltage potential, one of them we call source, namely whichever is sourcing the carrier and whichever is collecting or wherever it is draining to, we call it as drain. So, that is the naming convention. The controlling terminal you call gate, the substrate tap we call body, and then one of these two islands between which we are changing the characteristic, one of them we call source, another one is drain. Okay. Now, if you see the top view of this device, of course, whenever we are changing the characteristic of this channel, what we are trying to do is that we may be applying a voltage here, and then we will see how much the current it is flowing from drain to source. So, this current, whatever the current is flowing, it is of course, it is a strong function of whatever the distance we do have and whatever the orthogonal geometry, which means this geometry. So, the current device wise current is it is a strong function of this spacing called length of this channel, and also it is width of the channel. And why you call it is channel? Because as I said that once we apply the voltage here, current it is flowing through this region, that is why it is called channel. If you see the top view of this device, on the other hand, what you can see that we do have MOS structure here. So, this is the top view of that main portion. Metal it is working as gate, oxide it is working as insulator through which we are applying the field in the substrate region, and S stands for the body here, and in fact, that is nothing but the channel. So, you can see that channel portion it is only here, and as I said that the two important dimensions, one is the length and the width here. And these two islands are shown here. So, we do have one island here, in this case we call this is drain, and then we do have another island here, we call this is source, and in the top view we do have the this P plus island we call body. So, that is the basic structure, and I should say this is rather idealistic view of the basic structure. Though it is idealistic view, most of the time we will be referring this one. And just for your information, the rather realistic views are like this. The top view, if you see here, top view it is, so this is the channel portion. So, you can see the MOS structure it is here, MOS, but then the metal portion it is getting extended beyond this one. So, I should say the channel is of course, within this one, and its length is here and width is this dimension, and the controlling element or the electrode that is getting extended beyond this channel for reliability reasons. So, this part, the extended portion of the metal is basically helping to improve the reliability of the device. And then we also have something called connecting terminal. So, we do have this portion, it is referred as the contact, and on top of that we do have a metal. So, so likewise we do have in the drain region we do have contacts here, and then we do have the terminal metal. So, the box here, whatever the box we are referring here, it is, you may say that it is at higher level some metal. Note that this metal it is different from whatever the metal we refer. This metal it is for making the circuit in integrated circuit. So, likewise we do have the contact here, and then we do have metal. And in fact, in integrated circuit there are different layers of metals. So, typically this metal layer it is referred as metal 1 layer. So, in fact, this is also metal 1 layer. So, it is called met 1, and we do have the P plus region here for the body connection. So, here also we do have the contact and then metal 1. So, if you see the top view here, it is rather like this. So, if you take a cross sectional view along this axis, if I say that A dash, then you can say that the cross sectional view it will be similar to whatever it is shown here. However, it will be different, slightly different if you are looking for more exact interpretation. Say for example, in the drain region. So, the contact portion it is quite say thick here, and then on top of that we do have the metal 1. So, we may say that on top of that we do have the metal 1. So, this is the metal 1. So, you may say that this is metal 1 and this is the contact. So, this portion it is also metal, but it is getting implemented by different process steps. So, that is why it is referred as contact layer. Of course, its material is also different. So, we will not be going detail of that. So, likewise for the gate the source side also it is like that. We do have a contact and then on top of that we do have metal 1. So, we do have metal 1. Similarly for the body also and its corresponding metal 1 connection. So, here if you see along this A dash line, we are really not crossing this the contact of the gate. So, naturally we are will not be able to see. So, you may say that it is there. So, in our engineering drawing whatever the things it is not crossing, we may say that it is existing, but probably in different plane of the intersection. So, you may say that this metal 1 and the corresponding contact particularly for the gate, we are not really crossing this one. So, this is rather more I should say more realistic view of the cross sectional view of the transistor. And note that this oxide on the other hand, let me use different color. This oxide whatever we see thin oxide, this plays very important role, because we are applying a voltage here and through this thin oxide it is trying to influence the substrate in the channel region to change its characteristic. So, this is very important, but beyond this, beyond the this region channel region, whatever the portion we do have, in fact, there also we do have the silicon dioxide. In fact, everywhere here it is full of silicon dioxide. So, if you see the structure wise, it looks like it is a sandwich of the structure, and where you do have the controlling element, though we call it is metal, but actually this is polysilicon as I said. So, this is the gate, and everywhere as I said this is silicon dioxide. And so, this is just for your information. I am sharing this little realistic view. In fact, beyond this, beyond this device, if you see, which is part of a relatively bigger system in integrated circuit, we do have many more devices on this. So, you may say that this is the top surface of the substrate, and then we do have different devices, and on top of that we do have the contacts and metals to make the connection, and then everywhere silicon dioxide is there to isolate the device above the surface. So, likewise below also we do have the silicon dioxide. So, it is silicon dioxide is here as well. So, you may say that silicon dioxide it is also here, it is also here like that. So, that is rather more realistic view of the device. But for simplicity, of course, we will be using the simpler version of the cross sectional view, namely we will be using this so namely we will be using the so this cross sectional view we will be using. So, will let me so in our next discussion we will not be really using this clumsy cross sectional view. For simplicity of our analysis, we will be going for this schematic view only. So, this schematic view of the cross sectional you will be frequently referred to. So, there are few notes to be taken here. So, first of all, as I say that for further discussion we will be going to will be using this cross sectional view for simplicity. Then the substrate, you should be noting that substrate it is not purely complete insulator, it is rather weakly doped p type, and the device it is planar structure. So, you can see that the current is flowing horizontally, and access to different terminals, it is coming from the top side of the device. In fact, you may say that this entire portion it is the substrate. So, we cannot directly access this one. So, we have to use access through whatever we discuss, the contacts and the top the metal one and so on. So, all the access it should be from the top. So, and then the other thing is that in this basic structure we said that the substrate is p type, and by applying a voltage here we are changing this portion into n type. So, once it is getting changed to n type, we may say that channel it is getting converted into n type. So, that is why this device it is referred as n type MOSFET, or for simply we may say that n MOSFET. Okay. So, when you say n type, it refers to the type of the channel, the channel would be created. Of course, originally it was p type, but after applying the voltage here, the channel it is getting converted into n type. So, similar to this structure, there is also a counter device, or I should say counterpart of many circuits, and its structure it is very similar, but it is complementary in nature. So, if you see here the basic difference in this case for p MOSFET, the its body it is I should say body instead of substrate, we may prefer to say it is body. Body is weakly n type in contrast to weakly p type, and these two islands, drain source islands, they are p plus regions islands, and of course, to tap the substrate we require n plus region. To avoid the Schottky diode, we can have the ohmic contact. So, we will be later on we will be going further detail for in p type MOSFET. So, let we proceed with in MOSFET for further discussion, namely what we can say that the more detail about working principle, then IV characteristic and so and so. So, let us go into the working principle. Coming back to the basic device structure, and then let we also keep meaningful bias here. So, if we apply a voltage here at the gate with respect to substrate, and let you consider that this is also at the same potential, and try to see what kind of things are happening in this region. So, for the time being, let we also connect this drain region or the drain island together. So, in our whole circuit we do have only this source, we do have this source, and this source is gate to source. So, we may call this is VGS. So, we may say that this is VGS. So, if this VGS is positive, then let us see what other things are happening. So, if we apply positive voltage here with respect to source, and in fact, source is also connected to body. So, what we are expecting that since it is p type substrate, there will be holes as majority carriers, and because of this positive voltage they may be depleted from the surface region. So, you may say that whenever we are applying the positive voltage at the gate, it creates a field on the surface across this thin oxide, and as a result the holes are getting depleted. So, that is why we said that the holes are getting depleted from this region, from this channel region. And what happens, its effect it is that it is leaving behind negative ions. So, these negative ions are basically the stuck with the crystals, and they cannot move. So, they are basically working as depletion region of diode. So, these static ions, whatever the static ions are stuck there, of course, they cannot participate for current flow, but they are, whenever we are applying positive voltage, they are basically helping that the those fields are getting properly getting terminated to that. So, if I increase this VGS further, then what happens? So, if I increase this voltage VGS further, then whatever the holes it was there near the surface, that got pushed away. And then what is happening is, from the substrate region, the electrons, though they are minority, they are getting attracted. So, in case if you have this N plus region, in fact, most of these electrons may be supplied from this region and this region. So, as a result, in the channel region, we do have a thin layer of electrons. So, let me redraw this part again. So, we are applying voltage here VGS, and we want to see what other things are happening, particularly when the VGS it is sufficiently high. We do have the static ions, they are not participating for the current flow, and in addition to that, it is also having electrons. So, these electrons may be coming from these two islands. So, if you see the property of this channel region just below the oxide, its property is getting changed by applying this meaningful voltage. And as a result, what is happening is, more and more, while more and more electrons are getting accumulated here, it is providing electrical connection from this island to this island. In fact, that is what it is, as I said, it is making the conductivity from drain to source or source to drain, it is getting modulated by VGS. Now, if we of course, there is one important value of this VGS. Suppose this VGS it is reaching to a critical value called VTH. We will see what is the meaning of this VTH, such that the concentration of electron, whatever the electron concentration in the surface region, if it is exactly equal to holes concentration in the substrate, exactly equal to that, then we may say that the channel portion it is completely getting inverted into N type from P type, and its strength is exactly equal to the strength of the substrate. So, in other words, if VGS it is exactly to this critical voltage, you may say that this island to this island it is getting connected, and its strength it is defined by whatever the strength it is there in the substrate region. Of course, within the substrate region the majority carriers are holes, and here the majority or other carriers are electron. So, you may say that around this so around or beyond this point, you may, or at least at this point, you may say that the channel got inverted. So, if I apply this VGS beyond this VTH, then what you are expecting is that, of course, more amount of electrons it will be there, and then they will increase the conductivity of this region further. So, that is what I say, that further if you increase this VGS, then what you are expecting is that this portion the conductivity it will be more. So, then instead of really connecting the drain and source together or keeping this is floating, if we apply some voltage here, so you may call this is VDS, and then it is expected that since these two islands are getting shorted through this channel, the electron layer, then there is a flow of current. In fact, electrons are moving from left to right, So, these electrons are moving left to right, and the current it is flowing on the other hand right to left. So, that is why we call this current is flowing from drain to source. So, whenever we say the IV characteristic or characteristic equation of the device is nothing but this current, how it is changing with the voltage here VGS, how it is changing with VDS. Okay. Yeah, we are going to further detail of how the characteristic equation can be obtained in the next slide. So, here what we said is that suppose if we apply the voltage here VGS, and also we apply VDS, keeping body and source they are connected. So, we call this is VDS and this is VGS. The current it will be of course, we do have insulator. So, through this terminal there will not be any current, but then there will be a current flow. So, this IDS it is flowing here, and of course, this current it is carried by electrons. So, these electrons are really moving from left to right by this field or by this voltage. You may say this is lateral field. So, we can say this vertical field it is getting created by VGS, which is changing the concentration of the electron. On the other hand, the horizontal field getting created by VDS, which is helping for the movement of the electron from left to right, and as a result we do have the IDS. So, note that these electrons are coming from this side. So, that is why you call this is source, and it is getting drained to this terminal, that is why you call drain. Now, it is very clear that why you call this is drain and source. So, this current flow IDS, it is a strong function of this VGS VDS, and also it is strong function of the spacing from here to here, namely the length of the device. So, it is a strong function of the length, it is strong function of the other geometry, namely width of the device, and also it is strong function of the device parameter, which includes the thickness of this oxide, maybe it is referred as T ox, then dielectric constant here of this portion, it is referred as epsilon ox, and of course, the mobility of the electrons in the channel region. So, and that is what I said, that this IDS it is a strong function of all these things. And as a circuit designer, what we will be looking for, if the device it is already fabricated. So, W's and L's they are already defined, then we will be looking for the dependency of IDS as function of VGS and VDS. And as a device engineer, you may try to change this T ox, you may try to change probably in the surface, so that the mobility will be better, and so and so. So, as a device engineer, of course, there are different tricks to improve the device performance, but as a circuit designer we may assume that these parameters are given to us and we may consider they are fixed. On the other hand, if it is you are a VLSI circuit designer where the device yet to be implemented, however, technology is fixed, that means these parameters are fixed. So, you may say that whenever we say technology is fixed, device parameters are fixed, but then you also have the flexibility to change the W's and L's of the devices. So, for VLSI circuit designer, not only you will be playing with the applied voltages, but also the geometry of the transistor. So, in the next slide we will be going for the IV characteristic, but let me take a short break and then we will come back. Thank you.